Independence Day, 2016. Juno arrives at Jupiter and gets to work. The probe angles its high-resolution camera towards this stormy world. Juno's snaps do not disappoint.
The images returned from Juno are just beautiful.
Suddenly you have this magnificent mosaic of this planet. As a human being, I'm like, oh my gosh, look at this, it's amazing, this is coming back from Jupiter.
These are the closest ever views of Jupiter, a world 500 million miles away. But we didn't send Juno just to take pictures. One of its main goals is to peer deep into Jupiter's dark heart.
One of the big questions we have about Jupiter is, does it have a core? And you'd think, well, of course it has a core. Like every planet has a core. The Earth has a core. Everything does. Well, it turns out Jupiter might not.
Knowing what lies at a planet's core allows scientists to wind back the clock billions of years to the formation of the planets. If Juno can reveal what lies deep within Jupiter, it could change our understanding of how the gas giant formed. If Juno finds a solid core, it could mean Jupiter first formed as a rocky planet like Earth, then kept growing. But if Juno finds no core, it could mean that Jupiter skipped the rocky stage and formed straight from a cloud of gas. Answering this question could shine a light on other mysteries too.
If we can figure out how Jupiter formed, we can figure out the rest of the story of the solar system.
So how do you probe down into the interior of a planet when all you can really see are the very tops of the clouds? Well, incredibly, you can use gravity.
As Juno orbits Jupiter, it can sense in its orbit tiny little variations in the gravitational pull of Jupiter.
As Juno speeds around Jupiter, gravitational spikes tug on the craft. Turns out, some parts of Jupiter are denser than others.
If Jupiter were some solid ball, then as Juno passes by it, as it passes very close above its cloud tops, the orbit, the trajectory, would be very smooth. But in fact, if Jupiter has layers, or places where there's more mass and places where there's less, then it's going to pull on Juno a little bit differently.
Passing over areas of concentrated mass gives Juno a speed boost.
So what they do is, the engineers back on Earth can basically just say, how fast is it moving right now? How about now? How about now? And you build up a map of where the mass is in Jupiter underneath the spacecraft as it passes around.
Juno's instruments begin to map out the heart of the gas giant, revealing the mysterious core for the first time.
What Juno found was this amorphous mass, a fuzzy thing in the center of Jupiter. It's not as solid as we expected if it were just a metal and rock core, but there is something there.
In the center of the planet, Juno detects hydrogen and rocky material dissolved and blended together. It's a type of planetary core we've never seen before. Astronomers describe it as fuzzy.
We thought we were going to find an avocado. Instead, we found a bowl of chili. It's a hydrogen fluid chili con carne.
So none of our models of the interior of Jupiter turned out to be correct. That means we have to go back to the drawing board.
One theory is that Jupiter didn't form from rocks or gas, but from tiny pebbles less than an inch wide, strewn across the early solar system 4.6 billion years ago.
These pebbles came together, they accreted to form a massive object that was the sort of seed, the core of Jupiter.
The swarm of pebbles clumped together to form one giant core, 20 times the mass of Earth. But these pebbles can't sustain this growing planet for long.
Eventually, we need to make a jump from those centimeter-sized particles up to really large things, like 100-kilometer planetesimals, to really kickstart growth of a planet.
As Jupiter grows, its appetite becomes insatiable. The cores of other would-be planets are drawn in by its immense pull and absorb on impact, causing Jupiter's core to transform. Huge chunks of incoming rock are mixed up with gas and the pebbles that originally built the core.
We think that the core material that might have been there is actually dissolved and mixed in with the rest of the planet.
This mix of rock, gas, and pebbles leaves the core in a strange state, somewhere between solid and liquid, or, in other words, fuzzy. Once Jupiter's core reaches a critical mass, its gravity pulls in all nearby hydrogen gas, building the Jovian atmosphere, and leaving the fuzzy core trapped beneath thousands of miles of thick clouds.
And that is what formed Jupiter as we know and love it today.
Juno's discovery of Jupiter's fuzzy core could rewrite the book on Jupiter's early years. But Juno is just getting started.
We haven't even scratched the surface of the number of mysteries there are.
There's more to Jupiter than meets the eye, as Juno's instruments begin to reveal a darker side to this giant world.
Jupiter's environment is one of the most vicious in the solar system, and that's because of its incredibly strong magnetic field.
And Juno is caught right in the middle of it. The gas giant Jupiter holds clues to the mysteries of our solar system. And in 2011, NASA launched a billion-dollar mission to uncover them.
3, 2, 1, ignition, and liftoff of the Atlas V with Juno on a trek to Jupiter.
To reach its target, Juno embarks on a 5-year journey.
Sending any spacecraft to another planet is going to be tough, but sending one to Jupiter is really pushing things pretty hard.
Juno weaves through the solar system with extreme precision. The craft battles violent temperature changes and navigates carefully through the asteroid belt.
If there's a fleck of dust in your path and that thing slams into your spacecraft, it can do significant damage.
1.7 billion miles into its mission, Juno finally nears its target. But the probe is hurtling towards Jupiter at 165,000 miles an hour.
Juno is moving really fast. It's one of the fastest spacecraft ever.
You need to go fast enough to get there, but then you need to be slow enough to be captured by the gravity of that planet. You need to get it just right.
Entering orbit around Jupiter is the trickiest part of the mission. Get it wrong, and Juno could slam into the planet, or drift out into deep space.
To successfully get Juno to enter a stable orbit around Jupiter is almost the same as, say, shooting a basketball from London and having it land on the front of the rim in New York and just sitting there balanced. I could do it, but...
The red planet, Earth's neighbor, and the destination of NASA's most ambitious mission to date. But this expedition will be harder than we ever thought possible.
It hurts to think of how hard it is. It's the farthest a human being has ever been from the Earth. We gotta take every precaution.
As NASA's astronauts arrive at Mars, they'll face a huge obstacle. Landing on the planet is a daunting task. In the past, Mars hasn't always rolled out the welcome mat.
Mars is kind of like a graveyard for spacecraft. It's actually really hard to send something from Earth and land it on Mars.
This is how the European Space Agency hoped its $250 million Schiaparelli lander would touch down in 2016. But the lander's systems got it wrong. The parachute detached early, sending the craft into freefall for 33 seconds. Schiaparelli smashed into the surface at 335 miles an hour, leaving a deep black scar on the Martian landscape.
It turns out that Mars is actually a particularly difficult planet to land on. Even humanity's most brilliant engineers, we've got about a 50% success rate when it comes to landing on Mars.
The red planet is littered with dead spacecraft that didn't stick the landing. And for NASA's first crewed descent to Mars, the space agency must learn from these mistakes. But as the crew hurtles toward the surface, they're battling the same problem as all the landers that failed before. The Martian atmosphere is 100 times thinner than Earth's, so it can't provide the drag needed to slow a spacecraft down.
So it's not like the Earth where you can have these big giant parachutes that gently glide you down to the surface. You can use some of the air, but it's hard.
The red planet's thin atmosphere is a problem that's been billions of years in the making.
Mars doesn't have a large atmosphere because it's constantly being peeled away due to the lack of protection of a magnetic field.
The solar wind can strip away an atmosphere. On Earth, a liquid metal core creates a magnetic field, which shields the planet and helps maintain the atmosphere. Mars is different. 4.5 billion years ago, Mars and Earth formed from dust and gas in space. Mars forms where building materials were scarce. Its growth was stunted.
So Mars is much smaller than the Earth. It's a factor of 10 smaller than the Earth. And that factor of 10 in mass is important. All of that extra mass allows the inside of the Earth to stay warm and to have a core that's rotating, which generates a magnetic field.
4 billion years ago, the churning heart of Mars started to cool and solidify.
And with no hot core, there's no magnetic field being generated. All of the high-velocity charged particles coming from the sun pick away at the atmosphere and slowly tear it away.
We know it's losing atmosphere every second due to the solar wind. So, bye-bye atmosphere.
With little Martian atmosphere to work with, NASA had to be creative to get its crewless landers to the Martian surface. In 2012, the revolutionary Sky Crane landed the Curiosity rover using parachutes and retro rockets.
Previous missions have used both a parachute and something else, like a bouncy ball inflated around the spacecraft.
I don't think a human crew is going to be too pleased if they're going to be bouncing onto the surface in an airbag rolling to a stop, right?
To land people on Mars, NASA will need some new tricks. The 2020 rover will overcome the challenge with the Advanced Supersonic Parachute Inflation Research Experiment, ASPIRE. It will rapidly slow down the craft with the force of an airplane jet engine.
This is fine for the rover. It's actually going to work no problem, but it's not going to work for people.
A human lander will weigh far more than the 2,300-pound rover. Not even supersonic parachutes could land a crew safely on Mars. NASA will need a new plan. One idea is to use the thin Martian atmosphere in a unique way.
There's an idea of coming in really fast, getting to the thick part of the atmosphere, and then going horizontal to the ground and gliding and losing your momentum that way.
As the astronauts descend, they tilt the nose of the lander towards the Martian surface, aiming for the thickest part of the atmosphere close to the ground. Then they pull up at the last second, using friction from the atmosphere to slow the craft. Descent engines switch on for the final touchdown.
Is this a crazy idea? I mean, yeah, it's a little bit weird. I don't know if we'd really think about it doing something like this, but I mean, you've got to think outside the box sometimes.
Right now, NASA's plans for landing a craft on Mars are still on the drawing board. But even if they can get astronauts onto the surface, the thin atmosphere isn't done with them yet. It causes swirling dust storms that cover the planet's entire surface.
Mars doesn't just have dust devils, it has dust hell.
And these towering clouds have killed before. When the wind whips up this dust, it can have disastrous consequences.
The real problem is just that all these fine particles get lofted into the atmosphere, and it takes a really long time for them to settle back out.
And what the dust does is it just gets up in the sky and it sits there and sits there and sits there.
As more material gets lifted into the atmosphere, it forms huge dust storms. The storms are so large, they block out the sunlight and cool the Martian surface, creating a temperature difference between the ground and atmosphere that causes winds to increase and the storms to grow. And NASA's Opportunity rover knows firsthand the dangers of being trapped in one. Building a planet is no easy feat, with many tricky steps along the way.
Each one of these steps, going from dust grain to pebbles to planetesimals, takes a certain amount of time.
If Jupiter had to wait for distant rocks to collide and fuse, it would take 100 million years to form. And that's not possible, because our young sun attacks the gas in the protoplanetary disk.
A gas disk around a star can't last forever. The star is igniting and becoming active.
The clock is ticking. There's a young star in the middle, and young stars give off violent bursts of radiation, all kinds of solar storms, blowing away the cloud. So if you're going to be a giant planet, you have to move fast.
We know our protoplanetary disk only survived for about 4 or 5 million years. So we know that Jupiter was finished forming only 5 million years into solar system history. And that means we have to really jumpstart that process and get Jupiter to build a really big rocky core really, really fast.
Jupiter needs a giant core of rock and ice so it can grab nearby gas in the protoplanetary disk. The planet must rapidly build its core and capture this gas before it's blown away. To work out how Jupiter forms faster, we must wind back the clock to the earliest stages of planet formation.
So in our protoplanetary disk, we formed our first planetesimals, and we formed these out of all of the little pebbles that are out there in the disk. Now what? Still around its neighborhood and everywhere throughout the disk are a huge number of those smaller pebbles.
When we add these leftover pebbles to planet formation models, things go a lot faster.
Adding these pebbles to the mix, adding this to the models, was the big key.
These little pebbles can actually supply a lot of mass to these growing protoplanets. That's pebble accretion, and this is a method of actually accelerating the growth of early protoplanetary cores.
Now, when a planetesimal forms, it no longer needs another planetesimal to grow. it can feed on the surrounding pebbles.
So this planetesimal has some significant gravity. It can start grabbing nearby pebbles and growing by accreting them. And this planetesimal has a huge reach because of how slowly these pebbles are drifting by. So it can reach way out and grab a huge number of pebbles really fast, and that'll enhance its growth rate. And this first planetesimal can grow really, really fast, eating up all the pebbles around it.
It's a feeding frenzy. By gorging themselves on pebbles, planets can grow around 1,000 times faster than with planetesimals alone. But when we use pebbles to model the formation of the solar system, something strange happens.
Pebble accretion, when we model it, it can be so efficient and so fast that if you just start with a disk full of pebbles and they start making planetesimals, each planetesimal could grow to be something like the size of the Earth, really, really fast.
Instead of forming giant planets like Jupiter, you'd form 100 smaller planets like the Earth, and this is clearly not what we're seeing. So there must be something else going on.
To understand how the solar system formed, we need to look at how the growing planets interact with each other.
So your first object in your disk that starts growing by pebble accretion is going to grow really, really fast. But the next object is trying to form from the same disk, the same pebbles, but it's growing nearby the first one.
As the infant worlds grow, their gravitational pull increases. Larger protoplanets bully their smaller neighbors.
This really big neighbor can perturb its orbit, can shake it up and down, and by lifting them up and out of the disk, they can essentially starve them, keep them from accessing all of those pebbles to grow.
Once pushed out of the material-rich disk, the smaller protoplanet starves. The larger protoplanet thrives, gorging itself on pebbles and growing even bigger. Pebbles help explain how outer planets beat the clock and form before the sun blows the protoplanetary disk away. We calculate that by growing from pebbles, Jupiter and the other giant planets grew in just a few million years.
When we insert pebbles in our numerical models, our theoretical models, we can suddenly make these growth processes happen on those observed timescales.
Pebbles help Jupiter grow into the solar system's largest planet.
It can form the core big enough that it would very rapidly start to gobble up the gas around it and become the Jupiter that we see today.
The gas around an infant planet not only feeds its growth, it can push it through the infant solar system, which is not good news. Because giant planets on the move spell disaster for other growing planets. July 2019, we discover 4 strange planets. WASP 178b, 184b, 185b, and 192b. All 4 planets are gas giants. They're strange because they orbit their host stars at least 4 times closer than Mercury orbits our sun.
The physics on this is very clear. You can't form a planet that close to its star. You just can't get the gravity to attract enough material to do that. The star disrupts it.
Stellar winds, radiation, and the immense gravitational pull of a star should prevent any planet from forming where the WASP planets orbit. But looking around the Milky Way, there are hundreds more giant planets orbiting just as close to their stars.
It happens so often that it really took us back to the drawing board to understand what could actually drive that process.
Planets can't form so close to their stars, so we think they grow elsewhere and wander inwards.
This planetary wandering happens during the earliest stages in planetary formation, when that disk of gas and dust from which the planets formed is still there.
These gas disks outweigh all of the planets combined. There's thousands and thousands of Earth masses of gas. And those gases interact and push and pull on the planets with significant force.
As the planets grow, they clear a gap in the disk, and you create sort of an inner disk in the gap where the planet is and an outer disk.
So if a planet cuts a gap and the gas can't get through, all of that gas piles up behind it and just pushes. So you have thousands of times more mass than your planet pushing on your planet. It's like putting something in a flood, and it's just gonna overwhelm it and push it downstream. And the planets are just getting pushed downstream towards their star.
Could a migrating planet be responsible for one of the greatest mysteries of the solar system? Earth carries us on a wild journey through the cosmos. And clues to the effects of this trip are hiding in our own backyard. In New York City, amongst the buildings and traffic, we find moraines, rocks left behind by retreating glaciers. "18,000 years ago, a sheet of ice taller than any skyscraper covered Manhattan. Ice ages have struck regularly throughout Earth's history, putting our planet in a deep freeze.
There was a period in Earth's history several hundred million years ago, the snowball Earth period. We went through a very extreme glaciation, if you will, a very extreme ice age, where we think perhaps the entire Earth was covered in an ice sheet.
The trigger? Earth's orbital dance around the sun.
We tend to think of ourselves sitting relatively stationary on the Earth. It's pretty comforting, actually. But we're orbiting the sun at about 66,000 miles per hour.
Every day, Earth travels over 1.6 million miles on its journey around the sun. This orbit isn't always completely round.
Earth is generally going around the sun in more or less a circular orbit. But over time, the massaging of this orbit from the sun, from the moon, on the Earth's orbit causes the orbit of the Earth to change. So that sometimes it's an ellipse, sometimes it's more of a circle. Right now on the Earth, we're in kind of the most circular time in the orbit. So that means the summers are relatively mild and the winters are relatively mild. But imagine not that long ago in the past, it could have been really dramatically different. When the Earth is a little bit closer to the sun, maybe you have a really severe summer, and then on the other side of the orbit, you're a little farther away from the sun than normal, so you have a really severe winter.
Our environment is very, very sensitive to these things. And when the Earth's orbit is stretched out, that can actually trigger an ice age.
Our planet's 100,000-year orbital cycle caused the ice age that buried New York. And ice ages have had a big effect on human history. 15,000 years ago, plunging temperatures locked water away in glaciers and ice caps. Sea levels dropped, creating land bridges between continents. Humans migrated from Asia to America by foot. And for the first time, America was inhabited. May 2018, scientists revealed a whole new dynamic to Earth's journey. Every 405,000 years, our planet's orbital voyage stretches to the extreme, and Earth's planetary neighbors are to blame.
Because Jupiter is the most massive planet in our solar system, it is in many ways the bully on the playground, right? Its dynamics, its gravity, sculpts a lot of the dynamics of the solar system.
It actually tugs and pulls on the orbit of the Earth itself. It's responsible for some of the very changes that drive our climatic cycle here on our planet.
Jupiter isn't the only bully in the playground.
Venus is a fairly big planet about the size of the Earth, and it also comes closest to us in its orbit. So these two planets put just a little tiny elongation onto our Earth's orbit. And as this cycle continues, the more extreme it gets, we can actually notice a temperature difference that happens about once every 405,000 years.
Jupiter and Venus gang up on Earth gravitationally, pulling Earth's orbit into an even greater ellipse. Our planet's hot weather becomes hotter, and its cold weather gets much colder. Today, we're in a moderate part of the cycle, but in just 60,000 years' time, we could plunge into another deep freeze.
It's a little bit like a cosmic butterfly effect. I mean, even the smallest effects can have, big influence over time.
Earth's orbit around the Sun is just part of our far larger cosmic journey. The entire solar system is hurtling around the Milky Way, taking us places we don't want to be.
Sometimes our planet might wander into what's essentially a bad neighborhood.
What dangers await us? And could these neighborhoods spell disaster for life on Earth? Over the last 3.7 billion years, a series of extinction events wiped out almost 95% of all species on Earth. Now, research suggests our planet's orbit could be partly to blame, but not the Earth's orbit around the Sun. Our planet's larger and longer journey around the Milky Way.
Our solar system and our sun is shooting through the galaxy at about 537,000 miles per hour around the center of our galaxy. And that center of the galaxy is about 26,000 light years away, so it should take the sun about 230 million years to trace out one full orbit around the center of the galaxy.
Despite racing around the Milky Way at 500,000 miles an hour, Earth has completed less than 20 laps of the galaxy in our planet's entire history. And it turns out, this galactic ride is more complicated than it seems.
Now, if you look at the Earth going around the Sun, it defines an ellipse, but that's a flat figure. And you'd think, well, the Sun probably goes around in a plane as well. And it turns out, not that simple.
Most of the mass of the solar system is concentrated in the Sun. So, Earth and the other planets smoothly orbit our star. But the mass of the Milky Way is spread out unevenly.
That changes the gravity of the galaxy, and so it changes how things move in it. And in fact, if you give something a little bit of an up or down motion, it'll bob up and down as it goes around.
Riding the Earth is almost like riding a carousel. As the sun and the Earth go around the galaxy, the sun also goes up and down like you're on one of those horses with the pole. And so what this can do is take us into different galactic environments.
This bobbing motion takes Earth and the solar system on a 60,000-year journey, up and down through the Milky Way's galactic plane. Our orbit also takes us through different galactic neighborhoods. In 2018, planetary scientists were hunting for clues about the moon's violent past. They studied maps from the Lunar Reconnaissance Orbiter and focused on dark patches of the moon known as lunar seas.
The names we use for the features we see on the moon's surface are things like Sea of Tranquility.
And so before we knew what they were, astronomers would look at this and say, well, they look like oceans and seas. And that's what they called them. Mare means sea, and so you have Mare Tranquillitatis, which is the Sea of Tranquility.
But they're not seas of water, they're seas of lava.
Over 3 billion years ago, the moon was covered in vast lava seas, fed by giant eruptions of magma.
These patches that we see on the moon were lava eruptions which have filled in these basins. These are hundreds of miles across. These are enormous, much larger than even the biggest volcanoes on Earth.
If you were standing on the Earth 3.5 billion years ago, you'd probably see the glow of the individual lava flows flowing out across the surface of the mare.
We can work out how much lava flowed across the moon by measuring the lunar seas. But that's not all. The amount of lava in the seas can tell us if our planetary twin had an atmosphere.
Volcanoes on Earth actually don't just spew out lava. There's outgassing. Literally gas underneath the Earth comes out as well. And you get sulfur gases and carbon monoxide and a lot of other things. Well, the same thing happened on the moon as well.
The ancient lunar lava flows reveal that the moon's surface was covered in lava for hundreds of millions of years. The biggest eruptions happened around 3.5 billion years ago. They covered the moon in 200,000 trillion cubic feet of lava.
We estimate there was enough lava produced to cover the entire continental United States to a depth of 1/4 mile in lava.
Roughly 3 billion cubic feet of lava gushed out of the moon's volcanic fissures every year. These massive eruptions also spewed out around 10 trillion tons of gas, including water vapor and carbon monoxide.
It would be kind of a hellscape of erupting lavas. And then noxious gases would be spewing out of volcanoes. So all of this eruption of vast amounts of lava probably would have created an atmosphere around the moon.
It's still pretty thin compared to Earth's atmosphere, but maybe something on the order of maybe 1.5 times the density of Mars's atmosphere today. There may be just enough pressure there to be able to keep water liquid on the surface.
With an atmosphere in place around the moon, water vapor condensed into pools of liquid water. The thin atmosphere trapped warmth, preventing the water from freezing, creating a harsh but potentially habitable environment.
3 billion years ago, Earth had life. Is it possible that the moon did too?
This is not something that we have a lot of information about, but it's plausible because the moon certainly had a lot of volcanic eruptions that could have formed an atmosphere. So it is not a crazy thought to think there was a window of time where the moon was habitable.
But the warm, wet lunar environment didn't last. When the lunar volcanoes that replenished the atmosphere stopped erupting, the moon's weak gravity couldn't hold on to the atmosphere. In just a few million years, it was all gone. The surface water was lost to space. Temperatures plummeted. Any life died.
Even though the Earth and the Moon started out nearly identical from this same catastrophic collision, As time went on, they grew further and further apart, and they followed different life paths because the moon was small and cooled off. The Earth was large, was able to support an atmosphere, was able to support liquid water. The moon got none of that because it was just too small.
We thought that the moon's small size meant its molten interior cooled quickly, killing the volcanoes and stopping the core from generating a magnetic field. But new research suggests we may have gotten our lunar history wrong. In 2017, we re-examined 1 billion-year-old lunar rocks collected by the Apollo 15 mission and discovered something strange. The rocks had evidence of a lunar magnetic field billions of years after the moon's magnetism should have disappeared.
We've got a little bit of a mystery here. When the moon was molten, it could support a magnetic field. But the moon cooled off, and when it solidified, it should have shut off quickly its magnetic field. But samples from the Apollo mission revealed that the magnetic field hung on longer than what we think it took for the moon to cool off.
We thought the moon lost its magnetic field 3 billion years ago. But the Apollo 15 rocks show the moon had a magnetic field just 1 billion years ago. In 2021, scientists investigate something mysterious buried deep inside the Earth. It's a long hidden clue to our violent past.
Deep down 1,800 miles below the surface of the Earth, our core is surrounded by fluid rock. But inside that, 600 miles high and thousands of miles across, are two denser regions, and they kind of cup the core of our planet like two hands.
One of them is, half the size of Australia, for crying out loud. So, I mean, they're big lumps down there.
There's no reason they should be there. It's a mystery to us.
To solve this mystery, scientists need to examine the rocks buried over 1,000 miles beneath the surface.
We don't really know what these two big rocks are made of sitting there on the core. However, we've been able to sample them. How in the world is that possible? Well, these blobs are actually feeding mantle plumes that are rising up through the mantle.
So volcanoes in Iceland and Samoa, for instance, will dredge up some of these lumps of rock from the mantle. It's a precious chance for us to sample some of that deep rock that we'd normally not get a chance to see.
These rocks are old, very old.
It turns out that the samples in the lava that we think came from these blobs of rock in the mantle are 4.5 billion years old. That is as old as the age of the Earth.
So they tell us something about how the internal structure of our planet was arranged in the earliest days of the formation of our planet. So getting samples from that time is very, very important.
The age of the rocks may be a clue to their origin. They date back to a time of monstrous cosmic mayhem.
Four and a half billion years ago, the solar system was still a pretty wild place. We're approaching the end of the formation of planets. Earth would still be growing.
Back then, you wouldn't necessarily recognize the Earth. In fact, you wouldn't recognize the Earth at all. For example, no moon. The Earth did not have a moon when it first formed.
The young Earth orbits the Sun with other infant planets. One of them is an object scientists call Theia. And it's on a collision course with our home.
The Theia collision would have been a spectacular event. It would have been one of the coolest things you could possibly witness in the origin of the solar system, certainly the biggest event in the history of the Earth.
The Theia event is something that completely reshaped the Earth. The planet that the Earth was before the Theia event is gone forever.
The impact melts rock and throws out over 1 billion tons of debris.
During this incredible collision, these two planets were literally broken apart and combined into one big planet. Huge chunks of Theia stayed together as the now molten Earth began to form anew.
Now we can kind of paint a picture of where these big lumps of rock might have come from. They're very old. They're in fact the same age as that large impact event. They could be pieces of Theia.
The giant slabs of Theia sink down into our planet and lie undiscovered for billions of years. Earth reforms from the ruins of both planets.
Now, you might think that a collision like this is just devastating. There's no upside at all. But there are some things that came out of this collision that may have led to the possibility of life.
When these two planets combine, parts of Theia's iron core merge with Earth's.
So that means that Earth collected a much bigger core than it might have possessed on its own. This is good news for us because the core is the source of the magnetic field that protects us.
Liquid metal flowing around in the outer core generates Earth's magnetic field, a protective shield from the sun.
The sun can actually output billions of tons of high-energy protons and electrons in a single burp. That eventually would have stripped away our atmosphere. If it weren't for that active core and that magnetic field, we would look like Mars, just sort of a bare and barren desert.
Thanks to Theia's extra iron, Earth's molten outer core is large. So it cools slowly, staying molten, and keeps on generating a strong magnetic shield.
Because of that collision, the extra iron, the extra heat, we've stayed active. We have a magnetic field. We are protected. And in fact, that's why we're here talking about it.
The catastrophic impact helped life in other ways.
The Theia event was absolutely huge. Not an impact like a 100-mile asteroid making a big crater in the desert, but a planet hitting a planet, causing a huge disk of debris spread out from the Earth, out of which formed the Moon.
After the collision, the Earth tilts on its side and spins incredibly fast. A day only lasts a few hours.
The Earth itself rotates slightly on its side, and if left to its own devices, would in fact experience unpredictable, chaotic wobbling. The fact that the Moon is there stabilizes the Earth, stabilizes our climate.
The Moon's gravitational pull on our oceans creates tides and slows down the Earth's spin, creating a world primed for life.
We actually owe quite a bit to the Moon and Theia, its progenitor, for making Earth a hospitable planet for life.
A giant collision 4.5 billion years ago sounds like a catastrophe, but it was probably the best thing to happen to the Earth. Theia, I would shake your hand because we have a lot to owe you.
We also owe the science of chance because we lucked out with a 1 in a million impact.
If the impact from Theia had been a little bit harder, the Earth may not have recovered as well as it did, and we may not be here to talk about it right now. If it had been a little bit less forceful, then the impact of it may not have made the changes that we think were needed for us to be here now.
We got lucky. Most planets don't get to survive a collision like that and get a bonus moon out of the deal.
Earth's huge collision with Theia was not our planet's first brush with danger. An earlier explosive event could have stopped the solar system from sparking into life and the Earth from forming. There are a huge variety of moons orbiting Saturn. From Titan, a moon larger than the planet Mercury, to objects about the size of a sports stadium.
There must be something dramatic that happened to create a system that's so complicated and changing before our very eyes.
To understand such a marked difference in size, scientists look for clues in the moon's orbits around Saturn itself.
Most of the moons of that system orbit in the same direction. Well, that's obviously not a coincidence. That's motion left over from the formation of our solar system.
This suggests the moons formed around the same time as Saturn did. 4.6 billion years ago, the ringless gas giant grows from gas, rock, and ice in the protoplanetary disk, along with a family of moons. This origin story works for most of Saturn's moons, but not for the recently discovered objects orbiting in the opposite direction of the planet's rotation.
If there's a moon orbiting in the other direction, it couldn't have formed with the planet. It must have come from somewhere else.
Saturn captured these moons, but from where?
We think there was a huge upheaval in the solar system over 4 billion years ago, where the giant planets went from a close and compact configuration, started having interactions with each other, moved each other around to end up into the orbits that they find today. During that process, a lot of smaller bodies, like asteroids from the distant part of the solar system, got scattered every which direction.
During this ancient upheaval, Saturn grabbed some of the scattered objects. Many bodies now crowd the region around the planet. And that means collisions. Some are destructive. Others form new moons. In the cosmic pinball, some moons are thrown out of the system, and others into Saturn. Only one large moon survives the carnage.
Then all of a sudden, most of the mass of all the satellites is in that single moon Titan.
Titan may have formed from the material in the protoplanetary disk at the same time as Saturn, but then gorged on the debris created in the later lunar collisions. It amassed 96% of the material orbiting Saturn and grew so large that it developed a dense atmosphere.
When Voyager photographed Titan, it clearly showed that Titan had a thick atmosphere, which was so incredibly exciting. But it was so dense and impenetrable, that was all we could see.
2 decades after Voyager, the Huygens probe launched from Cassini and plunged through the murky depths of Titan's atmosphere.
Our first images of what the Titanic landscape was like were utterly and truly mind-blowing.
It showed there were mountains and there was sort of erosion on those mountains that looked like liquid had fallen down the mountains and brought material with it. That liquid must have come from somewhere, and where else than rain, than weather on Titan.
We've only found 2 places in the solar system with rivers and rain: Earth and Titan.
Out of this thick gloom, this is the most similar place to Earth we've ever seen.
Similar, but not identical. That rain filling lakes and rivers on Titan isn't water. It's liquid methane.
It's like if every oil well, if every gas station on Earth started leaking all over the place. That is what we see on this world.
The methane is a liquid on Titan because the surface temperature is 290 degrees below zero, which is a big problem for life, as we understand it.
We don't know of any organism that can really survive past -4 degrees Fahrenheit, and that's just because cells will tend to freeze there.
The cells that we have, what they're made up from, these proteins and fatty material, stop working and everything would die.
That's what happens to Earth's water-based cells. But could methane-based life survive in extreme cold? The ALMA telescope spotted a clue in Titan's nitrogen and methane-rich atmosphere.
With sunlight hitting the atmosphere of Titan, things like methane and nitrogen can get broken apart and reassembled like playing with Lego blocks. And then these molecules recombine to make new ones, like vinyl cyanide. Artist's depiction.
Used on Earth to make plastics, vinyl cyanide can build long chains of molecules, the type you need to build cell membranes. But unlike Earth's water-based cells, the extreme cold wouldn't destroy them.
It could survive at those low temperatures. So on Titan, it could be that this vinyl cyanide is able to form the membranes that are required for cells to develop, which are required for life to happen.
And good news, there's a lot of this stuff on Titan right now.
There's as much as 10 billion tons of this vinyl cyanide in just one of the lakes. If you wanted to start making creatures out of it, say, I don't know, giant squid. Do you like giant squids? I hope so, because you could make billions of giant squids out of this vinyl cyanide.
Saturn's geyser moon, Enceladus, could have life as we know it. Titan might have something truly alien.
It is an unrelentingly brutal, cold place compared to Earth. But for Titanic life, it might just be ideal.
As we search for life beyond Earth, it still comes with a bias of life as we know it. And so it's great as we continue to explore and continue to evolve our definitions, we can expand our view of how to search for life.
Maybe the Saturn system has 2 living worlds.
But for life to thrive on Titan's surface, it must survive a storm of deadly particles racing out of the sun at over 1 million miles an hour.